Welcome back. Previously, we implemented the full proof of work system that is going to require miners to put in computational work to discover a valid hash for a block. By adding a difficulty criteria to the valid hash, the miner will have to keep generating valid hashes until one with the proper number of leading zeros is found. Right now, the difficulty in our system checks for leading zero characters on a hexadecimal hash. However, Bitcoin is a bit more fine-grained. It uses the binary equivalent of the hash and checks for leading 0 bits. To demonstrate why this is useful, go ahead and search for a hexadecimal to binary converter online. You'll probably find this binaryhexconverter.com site, and we want to go to the hex to binary converter page. Alright, let's experiment. Let's try the value 00ABC for the hex value. And what we have as the result is a binary value with 8 leading 0 bits in the binary equivalent form of the hex value of 00ABC. So that's definitely more room for a higher difficulty value than the leading 2 0 characters in the hexadecimal form. In this case, we can go all the way up to a difficulty of 8 leading 0 bits. So what about 1 ABC? Let's try that. And in this case, we get a difficulty of 3 leading 0 bits here. So we can even check for difficulty values on hexadecimal to binary equivalents in the binary form when we don't even have a leading 0 character in the hex form. And this is why the binary form allows us to be more precise. Even when the hexadecimal form doesn't have leading 0 characters, its equivalent binary form could have a qualifying number of leading 0 bits. So in this case, the hex value of 1 ABC could satisfy a difficulty of 3 for the leading 0 bits value. Now, we could go ahead and implement the binary hash proof of work system right now. But for something like this, it's nice to have a more hands-on proof and experimentation process to see if this alternate implementation with the binary value is indeed more optimal. So let's write a script that is going to give us the average pace of mining when we try to add many blocks to the chain. And then we'll check out how this script performs with the hexadecimal value for hashes versus the binary value for hashes. That way we'll be able to see the difference between the two. Okay, in this case we actually won't use test-driven development though, because we'll be writing a script purely for experimentation purposes and not core application code. Alright, let's head to the project. We're going to make a new file in the project called average-work.js. Cool. And in this file, we're going to want to make an instance of the blockchain class to experiment on. So first up, require the blockchain file from the local blockchain project. So we have the blockchain class from the local blockchain file. And then we can create our blockchain instance, which is a new instance of the blockchain class. Nice. And then we'll add an additional block. So we'll be basing our logic based on differences of timestamps between each new block that was added. We're going to add this initial block so that way our code will be based off of current timestamps rather than that Genesis data timestamp, which is completely old and set to 1. By the way, as a side note, timestamps in JavaScript are based off of counting milliseconds starting from January 1st, 1970. So 1 as the millisecond value for the Genesis block would really throw off our data because that's so far back into the past. But anyway, let's add that block that consists of data, and that data will mark this as the initial block that we're experimenting with. Cool. Next, let's create some variables that we can work with in this experiment. Something that we want is a prev timestamp, so previous timestamp. We'll track the next timestamp. We'll track the next block, as well as a time difference between the last block and a new one. And then overall, we're going to keep track of the average time it's taking to mine blocks. We'll also keep track of all the times in a times constant array. Cool. And then let's mine 10,000 blocks. Each time we mine a new block, we'll keep track of how long it took to mine the block using the difference between the previous timestamp and the next timestamp. We'll also use the overall times array to keep track of the average times it has been taking to mine all blocks. So if the proof of work system was implemented correctly, well, this average time should eventually converge to the mine rate that we set for the overall system. So that'll be another thing that we check in addition to seeing the difference between the binary hashes and the hexadecimal hashes in terms of how they perform. So let's make a loop that goes up to 10,000. So that is 4 0 digits after a 1, I++. Cool. And first up, we're going to track the previous timestamp. So we'll set the timestamp to whatever is the last block in the current chain. We'll access blockchain.chain. We'll find the last block by looking at the one at the last index. So that's blockchain.chain.length -1. And then we'll get its timestamp. And then let's go ahead and add a block with unique data. So we'll add blockchain.addBlock. And the data can be a template string that says block, and we'll also insert the I variable just so that this block has some unique data for its block. So the template string has backticks, and then for interpolation, so variable insertion into the string, it's a $sign and then curly brace syntax around the inserted variable. Cool. So now we can get a reference to the next block, which similarly is now the last block in the chain. So again, we'll do blockchain.chain.length -1, and we're accessing that block within the blockchain.chain. The next timestamp variable is going to be this next block's .timestamp. Very cool. And this allows us to track the time difference. So we're going to get the time diff, and this is equal to the next timestamp minus the previous timestamp. So this is how long it took for us to mine that new block. And overall, let's push this time diff to the overall times array. Very nice. Finally, we have the average to calculate, and that can be calculated by summing up everything within the times array and then dividing that by its length. So let's actually shorten this to make this a little cleaner. These two can be grouped, so that looks nice and grouped. And overall, we want to get a sum of everything in the times array. And to get a sum, we can use the JavaScript reduce function, which reduces the entire array into a single value. That single value is kept track of in a total field, which is the first parameter of a callback function. And then this second argument to the callback is what we're using one item at a time within the array within the callback. So at every iteration of this array for every item, we're going to add that current item number to the growing total. So this overall is going to reduce the times array to a sum by adding each individual number in the times array, or rather the times array, to a growing total. Cool. And from that sum, well, we can divide the times.length to get the true average. Cool. So that does enough. It gets the previous timestamp, adds a block, finds that next block, gets the next timestamp, does a time diff, pushes that time diff, and then finds the average. The last thing that we want to do is we want to log our results so we know what's going on. So let's console.log a template string with a pair of backticks. This message will say time to mine block. And the time to mine that block is the time diff, and this is keeping track in milliseconds. We'll also want to log the difficulty so we can see how the adjust difficulty mechanism is working. So we'll look at nextBlock.difficulty. And then this is going to be a pretty long message, but we also want to see the average time, which we'll do by inserting the average variable, and this is also in milliseconds. So make sure you have that entire string. Here, I'll scroll through it so that way you can see it. All right, very cool. And make sure you have all of these changes. And once you're ready, go ahead and save the file. All right, and once you have that, you'll want to head to the command line. Open up a second tab, and then fire node averagework.js. So as we do so, you'll see that the initial difficulty matches what we set in the config.js file. And as new blocks are added, the difficulty is either raised or lowered by 1 each time. So it goes all the way up to 5, but it often drifts back to 3, and most of the time it's around 4. But overall, the average time is increasing. We want the goal to get it to 1,000 milliseconds overall. So I'm going to use the power of editing to time travel a bit to when my script has run for a while. So I suggest pausing the video for about 3 to 4 minutes until your average time has had a chance to run for a while as well. All right, welcome back. So hopefully your results look around the same as mine. My average time has been hovering around 670 milliseconds for quite a while now. So why is that so? Isn't the mine rate 1000 milliseconds? Shouldn't that be the average mine rate that we're seeing output over here? Well, in this case, Node.js and the operating system is just a little too powerful. Because of our leading zeros implementation, the difficulty gets to a low requirement too often. Values of 2 or 3 are quite low for a number of leading zeros. This, in addition to the relatively low mine rate, gives the CPU many chances to discover a valid hash very quickly. Instead of this result of hovering around 670 milliseconds, ideally we would have wanted to see the average time hover around the set mine rate of 1000. So perhaps a more fine-grained system for the difficulty adjustment could give us the help that we need. And a system that uses leading zero bits with binary hashes instead of the current hexadecimal hash could potentially offer that. So let's do a leading zero bit implementation with binary hashes next.